The main seminar by Professor Lilian Bossuet. While he's setting up, let me just introduce him. Thank you, Lilian, for coming all the way from University of Saint-Étienne near Lyon. Lilian is a full professor there, largely works in the security space, and he's also the head of computer science department at Current Laboratory. And as I learned recently, he's going to be also the deputy director for the lab from January next year. So very thankful to him for coming, spending his time and visiting us. So Lilian, all yours. You need some help with the, yeah, it's there.
Okay, hello everybody. First, it's my pleasure to be here today. It's a great honor for me. And firstly, I would like to thank my friend and colleague Kuran Bati for this invitation and give me the opportunity to try to give you an overview of the work of my team about the security evaluations of complex and heterogeneous system and chip. But just before to begin this presentation, two words about the cities I come from. So Saint-Étienne is on the southeast of the France. It is not a big city, but it's a bit larger than Exeter. And it's the same thing for the university. So the University of Saint-Étienne is called the University Jean Monnet, and the site of the university, I think, is the same site as the University of Exeter. So there are different campus in function of the scientific field studied in each campus. So I work in the campus called Manufacture. Is a French word for factory, because in fact it was the old weapon factory in France. Now this factory is closed, and so the building become a university, and I think that is a good destiny for this place to go from the weapon factory to the university. And so in France, the research is structured by laboratory. So I work in a laboratory called Ubercurien. It's a joint unit between the French CNRS, so it is National Center for Scientific Research, and the University Jean Monnet, and there are around 300 people in this working in this lab. Half of the people work on the physical aspect of the light. There are some experts of laser, etc. And the other half work on computer science, mainly on machine learning, image processing, and the security of embedded system, and it is the case of my team. So it's my team, we are around 28 people. In fact, it is a larger team in France that work on the field of hardware security. And you can see the different the main topic of my team work. So we work on the physical attack and countermeasure. What I mean by physical attack is the way to use, for example, laser or electromagnetic signals to perform fault injections inside the integrated circuit. We work also on side channel analysis, when, for example, by performing the measurement of the power consumption of an integrated circuit, we can find some information, sensitive information from the circuit. We also have a very historic and great experience on the design and characterizations of random generations inside the integrated circuit. It's not really easy to be able to generate true randomness inside with electronic circuit, and so we have this expertise. We work also on the software and hardware secure implementations of classical and post-quantic cryptography chain. And last but not least, we work on the security of heterogeneous system on chip. And it is that I would like to present to you today. So perhaps the first things is to explain you what I mean by complex and heterogeneous system on chip by giving you an examples. It is the example of that we call SoC FPGA, provided in this case by AMD Xilinx. In such system and chips, we can find very different things. And the first look at the architectures of these systems, we can really understand that these very complex systems. There are two parts, a blue part and a yellow part. The blue part is called the processing system, that we call also the software part of the system and chips. As you can see, it is too small, but in fact there are several processor core inside this system and chips. In this case, there are, for example, 4 ARM core for the general application unit, 2 ARM Cortex R5 for the real-time processing unit, and also one unit dedicated to graphic processing. So even for the processor embedded in these systems, there are some heterogeneous because they are not the same, all the same processor core. We can find also several memory, hardware accelerator in this part. And the second part, the yellow part, is the classical FPGA parts, that's to say the programmable logic part of the system in chip. And so they are in the same system, software resources, hardware resources, memory, etc. So that is really interesting for a lot of application, like for example for cloud computing. It is possible to run such a system by using Amazon services, for example. Amazon send FPGA as a services with such systems. This kind of system chip are used for automotive applications, spatial defense, etc. Okay, but when we use this kind of system, for example, for defense or spatial applications, etc., it's required to execute some sensitive application, for example, cryptography function, etc. And so it could be a very interesting target for malicious entity, so for different attacker. And the issue with such a system is the complexity of the system, and that I would like to show you today. That in fact to be too complex is the same thing that to be too vulnerable. Because in fact it is possible to for an attackers to take benefits of several vulnerability from the software resources, from the hardware resources, and by using together all these different vulnerability, it is possible to attack inside the SoC some part of the SoC to obtain sensitive information, for example. Okay, so to show you all this capability for the attackers, I will use during this presentation a sample systems, but it's based on this system in chips. So we can find the blue part, the processing part, the yellow part, the programmable logic, and in white the memory. But you can see also that there green part and red part. That is because, in fact, if you want to secure such an application with ARM processor, it is possible to use a security technology provided by ARM called trust zone. So it is a software isolation, and as such, it is a first interesting security level to have to obtain isolations between some software applications. So it is possible to split virtually the architectures in two worlds. A normal world for most of the application, in fact, is here in red, or a secure world for the sensitive applications here in green. So normally the trust zone technology is used only by the ARM core, but with such a system on chips, it's possible to extend the trust zone from the software part to the hardware part of the systems. So it is also possible to dedicate some hardware resources to the normal world in red or to the secure world in green. So all these systems normally work. When an application is executed in the secure world, this application could have access to all the resources of the system, including secure hardware resources or non-secure hardware resources. And if the application is executed in the normal world, the application can have access only to the non-secure hardware resources, and the same thing for the memory resources. So we have prototyped this sample architectures with a CAD tool provided by Xilinx. Okay, so we can try to see first solutions to perform the corrections of the trust zone security provided by ARM when this security is extended from the software part to the hardware part. In fact, the thing to know from the ARM core to know which word is used at the time key. In fact, the information is provided by a sample bit called the NS bit, just 10 or 1, to say if the software is executed in the normal world or in the secure world. And this information is sent to the hardware part to know also the security level for certain times. And these informations go to the AXI ports that perform the connection between the processing system and the programmable logic. So the first thing that we'll try to do is to find this information inside this port and to know if it is possible to change this information. So we have found that NS bit, so the bit that informs the system about which word is used, in fact, could be found in one signal of the AXI protocol called HW And in fact, it's really easy to change this information. There are several solutions because it's only one bit of information. So between the two interfaces, so it's in French, the master interface and slave interface, we can find the signal at W approach. And for example, at just a simple logic gate, so it's what we call malicious hardware or hardware Trojan, for example. It is possible to directly cut this signer if you want, or use several solutions to change the signal. So from the hardware point of view, all these solutions as only samples is require a few number of hardware resources, even no resources, for example, just got this signal. And with these sample modifications, we can completely change the security of the system because, for example, if an application is running in a non-secure world, it is possible to change the information of the secure world, of the information about which work is used, and for example, to give the access to the non-secure applications to some resources dedicated, hardware resources dedicated to the secure world. And in the opposite way, it is possible to perform some denial of services attack. By changing even when an application is executed in a secure world, and the possibility to have access to some resources. So it is really powerful because in fact we completely change the security level of the systems. So the question is now how to realize this modification on the designs. So what we have proposed as scenario is that in fact it is possible to corrupt the CAD tools used to design the systems, because in fact, so the CAD tool used to design the system with the system on chips are in fact non-secure. Most of the CAD tools are vulnerable to malicious software corruption. So the scenario is two things that malicious software can affect the computer of the designers, and after, when the designer design the systems, it is really easy to change the design by manipulating the TCL script. So it's simple script used by most of the CAD tools, and the malicious software can add some line in this TCL script, and even for the designer, it's not possible to see the modifications produced by this line. So at the end, the designer provides the design, and there are, for example, an hardware trojan or some things inside the hardware able to perform these modifications of the security. So it is really powerful, and for some company, I can say you that it's really a credible scenario. For example, for airplane designer, for example, I know that there are exactly this security issue in mind, and we are not the only one that have tried to say that there are some security issue with the CAD tool used for FPGA and SoC FPGA. So that is the first conclusion, that in fact the trust zone technology security isolation provided by ARM could be efficient for the software point of view, but the extensions of this technology through all the heterogeneous SoC is completely vulnerable and easy to corrupt. Okay, other things is the possibility to perform attack by using malicious hardware IP. So in fact, to try to accelerate the design steps, most of the designers use hardware IP provided by several providers in the world. but it is really difficult for the designer to know exactly what are embedded in the hardware functions that they can obtain. And sometimes it's possible for this hardware IP to embed some malicious systems. And what is possible to do with such corrupted or malicious hardware? What we find for this kind of system, and that it is possible to have a direct access to the memory by manipulating the memory controllers. And that is also really powerful because, for example, despite of the trust zone security managed by the ARM core, an hardware IP can have a direct control to the memory controller. And if the attacker performed previously a reverse engineering of the memory to know the memory mapping, it's possible to target the configuration registers of the trust zone technology and to change all the information about the memory mapping, for example, to know which part of the memory is dedicated to the secure world or the non-secure world. So it is really easy and powerful tool. And in fact, other colleague in Europe in the team of John Sick at TU Munich have shown that by using the same system, it's possible to break the secure boot of such systems. Okay, so it is the second conclusion. Now I would like to show you other possibility of attack. First one is a way to perform timing analysis attack on cache memory from the hardware part. So all the hardware part of the system is able to analyze the cache access performing by the software applications and then be able to attack this application as practice I just presented you before. So I remind you that in fact the side channel analysis is the capability for a malicious agent, malicious software, or malicious hardware to perform measurement from a physical measurement of the side channels and be able to retrieve some information due to the leakage information of the victim inside these side channels. So it is possible to perform such attack by the measurement of the power, the supply voltage, for example, or the electromagnetic emanation of the system. But it is also possible to perform by analysis the time access of the shared cache memory. So is that in practice showed you before, and the principle of this vulnerability is based off the cache memory architectures of modern system on chip and multiprocessor system on chips, like in Intel architecture, for example. Because there are several levels of cache, and one is shared between all the processors, when software applications try, for example, to load the data from the external memory, this data will be stored in the L1 cache, for example, but also in the low-level cache. And so from the attack point of view, from the malicious software point of view, it's possible to obtain information from the victim. So I would like to show you this principle just here. For example, if one applications running cryptography function, for example, try to have access to instructions, and so to load the instruction, if the instruction is not already in the cache memory, they come from the external memory. So the time to obtain this instruction is a bit long. And for the attacker point of view, if the attacker wants to know, so it is also a software, want to know which instruction was used by the victim, you have to try to have access to these two instructions. And for the instruction 1, for example, because the instruction is already in the memory, commit to the cache hit and fast access to these instructions. And for the other one, as this instruction is not in the cache memory, to the cache miss, and the time to have access to the instruction is longer than for instruction 1. So the malicious software can have an information that the instruction 1 was just used by the victim application, and at the end to be able to obtain all the instruction sequence executed by the victim. That could be really interesting from some cryptography functions when the instruction executed depend of the sensitive information like cryptography key. It was the case for the naive implementations of public key cryptography, for example. It's also possible to, so in this case, when the instructions executed depend of the sensitive informations, but it could be also used for targeted symmetric cipher, like EES, for example. Some implementation of this algorithm when this application is running, the address used to obtain some partial result inside the algorithm, the address reading is related to the key. So if the malicious software has information about which address is loaded inside the external memory, directly some information about the key. Okay, so this is a classical attack, what it is possible to do by analyzing the cache access. And now the questions for the heterogeneous system and chips, if to know if it is possible or not to perform this kind of analysis from the programmable logic. Because most of the attacks in the literature are directly from one software application to another software applications, but we would like to know if it is possible from the hardware point of view. So in fact, it is also possible by using one dedicated core called ACP in this case for accelerator currency port, and this port gives the access to the programmable logic to the cache memory of the processor cores. You can see on this slide the cache memory architectures. So there are the two processor cores. In this system on chips, there are only two levels of cache. So there are the cache L1 dedicated to each core, and the cache L2 here. And in fact, the FPGA, by using the ACP port, can have access to the new control unit and the FPGA can know if a data or instructions are or not in the cache before to have access to the DRAM. So we know that it is possible, but to perform the attack, the attacker must to be able to distinguish a cache hit from a cache miss. So to do it, it is possible to probe some of the signal available on the AXI port. So this is different signal, and here we can see, for example, the difference between a cache miss and a cache hit. So there are a time difference, and it is possible by using counter in the hardware part of the systems to distinguish the cache miss from the cache hit. And it is that we have proved. And so by using it, we can perform all the cache memory side channel analysis attack like known in the literature, and present it first for a software attack. Now it is also possible to perform it from the hardware part of the systems. So we show that, for example, with ERS crypto algorithm, it is possible to attack this implementation, this software implementation for the hardware part. Okay, so now other things also interesting from the systems is the possibility to perform transmission, discrete transmission of information by using what we call covered channels. And to do this transmissions, we propose to manipulate the power management system of the system in chips. All the system in chip now embed power management systems, and it is possible to use it to corrupt the isolation, for example. So in the case of the covered channel, it's something close to the side channel analysis, because we also use a physical channel, but this time there are one senders that perform physical coding of the informations on the covered channel, and one receivers able to perform the measurement of the information on the covered channels. So it is possible to use several physical channels, like again the supply voltage, the clock frequency, also the cache, the time access to the cache memory can be used also to perform a covered channel. But I would like to show you how to use the clock frequency. So we use something called the dynamic voltage and frequency scaling available in this SoC for the power management of the systems. So this DFSS system are used to try to fine-tune the point of functionment, is to say the voltage, supply voltage, and the frequency, to try to have a minimum energy consumptions, and to adapt the frequency, the energy, and so the frequency and the power voltage exactly to the different tasks of the systems. But this can be manipulated to perform some attack. So the first one was presented in 2017 by some colleague from the University of Columbia. And so this attack is called Clock School. And so they showed that it is possible to change the frequency regulator, so the frequency of the systems, to perform some clock glitch, and to inject fault during the execution of a crypto algorithm performing by hardware crypto accelerators. Same years, other colleagues from the University of Texas proposed a way to use this frequency modifications to have some covered channel between software core inside the SoC, and we add other possibility for the attacker, is the possibility to have a covered channel from the hardware part and the software part, but also to have a covered channel inside the SoC from outside the SoC. So I will show you just before how to do it. So it's all the same systems. that we try to do is to manipulate the clock controller. And it is possible to manipulate it from the processing system, but also from the programmable logic part of the SoC, and so to have several cover channels from software part to the hardware part, from the hardware part to the software part, but also from the software and the hardware part to outside of the SoC. And I will show you how to do it because it's really easy to visualize it. So for these things, we use a really simple frequency modulations called BFSK, is binary frequency scaling. We use only 2 frequencies. So there are several solutions. It is possible to use one frequency to send 0 and another frequency to send 1, for example. But in this case, we use the same frequency for 0 and 1 for the 2 informations, but the durations of the symbol is not the same. That we have here. In fact, we have a first frequency for to transmit a symbol. The symbol is 0 or 1, but the duration is not the same for 0 or 1. And there are a second frequency used for inter-symbols transmissions that it's used to be able to perform the separation between one bit and another bit. And then how to obtain this information from outside. In fact, it's really simple. It is possible by using a simple electromagnetic near-field probe to probe the electromagnetic emanation of the system in chips and to perform the measurement of the internal frequency. By using real-time spectrum analyzer, it is possible to have directly on the screen the information transmitted by the circuit, by the system in chip, like I can show you here. So here it is the amplitude of the spectral ray at the transmitted frequency, and so we can see that there are the transmission of binary information 0 and 1, and that the symbol duration is not the same for 0 and 1, for example. So we can use exactly the same modulation inside the SoC, but it's just to show you that it's also possible from outside. Okay, so we have proposed in these publications other type of frequency modulations. It's possible to use several possibilities. It's really open, and we have shown that it's possible even with the more recent system in chip provided by the Xilinx, for example. Last things is now the possibility to perform some side channel analysis by performing the power consumption measurement inside the SoC. So I'll remind you what is the side channel analysis. So I've already explained you, but this time that we would like to do is to be able to perform inside the SoC the measurement of the supply voltage fluctuations. And it could be interesting because, in fact, these systems share power distribution network is used to provide the power inside all the system. So if the malicious software or hardware is able to performing the measurement of this fluctuation, it is possible to obtain some information on the leakage from the victim. So what it is possible to do in this case, so the measurement is performed from the hardware part of the system by using some sensor, and I will show you just after how to design this sensor. So it is possible to classically attack the cryptography algorithm executed by an hardware accelerator, but also in software. It's possible from this part to attack both software and hardware part. It's also possible to attack the implementation of deep neural network, even in software or hardware. So what we can perform is reverse engineering, for example, of this neural network to know or to obtain some information on the hyperparameter of the system, of the network, but also to have information on the input data or output of the network. And it's also possible to perform disassembly of the software executed in the software part, or when we use some synthesized processor like a RISC-V, for example, from the hardware part. So how to design this sensor? In fact, it's well known in the literature. Most of the solutions propose to use this kind of sensor called TDC, because in fact what we have to do is to design a system able to perform a conversion from the voltage to time, and after to be able to perform the measurement of this time. It's exactly that it's possible with this kind of sensor. It's something really simple, and we have binary information by the measurement of the Hamming weight of this output that is dependent of the voltage of the systems. And if the voltage increase, for example, there are more run in the outputs of the Hamming weight is higher, or lower lower when the voltage decrease. So this kind of sensor is really efficient, but there are some drawbacks. The first one, you can see, for example, layout of the FPGA part of the SoC. In green, it is, for example, the victim, the AES hardware implementation of the EES. And here in red, it is sensor. So we can see directly that the size of the sensor is really big in comparison to the victim. It's not really discrete. Moreover, in fact, the performance, the resolution of this sensor is good, but the performance is not really high. And so we have proposed something really better, is to use a simple logical multiplier, so designed with logic gate. And in this case, we can force the output of the multipliers to change from all the bits at 0 to all the bits in the input at 1. And the issue of this, the limitation of this logical circuit is that it's not possible to change in the same time all the bits from 0 to 1. It is due to the propagation delays inside the logic gate used to design the multiplier. And in fact, these propagation delays depend of all the voltage, the supply voltage used to assert the power of the systems. So we have shown that it is possible by managing the time need from this multiplier to change all the bits of the output and to perform the measurement of the supply voltage fluctuation. Okay, so this sensor could be embedded in the malicious hardware IP, and it is possible by using this sensor to attack the hardware implementation of the cryptography function or the software implementations. This is the efficiency for the two implementation, the two victims. And so For example, when the victim in the hardware implementation, we can see this time that the size of the sensor is really small in comparison to the TDC just I've shown you before. And the efficiency of the sensor is clearly better. So we show that it is possible to find all the bytes of the secret key of the AES inside the system and chip by using this sample sensor. Also, we have proposed something more. In fact, in the literature, when the people propose to use a sensor like this one or TDC sensor, they always need to have triggers to begin the measurement and to perform the alignment of the measurement traces. And so the trigger has to come from the victim. So it's not really a good thing to say that the attacker has to ask to the victim to say hello when we want to be attacked. So we have proposed to use, in fact, the capability of using cover channel, like I'll show you by the manipulation of the DVSFS systems. And so, for example, in this scenario, there are two malicious parts in the system. One in the software and the sensor are embedded in the hardware. So the attack comes from this malicious software. So they ask for a crypto function, and then it can change the frequency to alert the sensor and to send to the sensor that they are to begin the measurement of the power supply supply voltage fluctuations. So it is something interesting to think that, in fact, because the systems are complex, it is possible to imagine also complex attack paths by merge malicious software and malicious hardware, for example, and to try to use the vulnerability from software and hardware both. Okay, so now to conclude this talk, so I've mainly present you the work of my team, but in the state of the art there are a lot of proposition of inside attack to perform fault injections or side channel analysis. There are someone really know, like Rohammer, for example, has the capability to inject fault by manipulating the DRAM, the memory. So by using a dedicated malicious software, it's possible to perform physically modification of the DRAM. So it's really interesting. There are several propositions, and all this work show that, in fact, this kind of system and chip are designed first for the performance and for the heterogeneity, but not for the security. And at the end, as I've already said to you, too complex is something that too vulnerables, and it is really important for the designer to understand that this kind of heterogeneous system and chip are really vulnerable to a lot of attack. And so we need to propose new architectures designed for security. That is really important, and to propose mitigation for the designers. So it is what we try to do in my team. We begin to propose some architectures like this one, but I will not present you this now. We work also on the way to propose new trust execution environment that can to take benefits from the hardware and the software, and to see, for example, the security isolation not only from the software point of view and not only from the hardware point of view, but try to see both the software and hardware isolation in the same time. And I'm sure that it could be possible to have some common work with you, with Current, for example. There are some European programs that try to propose a new system software and computing architectures more secure and protected against more or most of the vulnerability in attack. Okay, that's all. So